Hi everyone, and welcome back to Educator.com. I'm Dan Fullerton, and today we're going to start our work by going through the 1998 AP Physics B examination. And you'll find the link below where you can go print out a copy of the examination. And before we get into the test itself, I'd like to talk a little bit about how the test works. You have two parts to the test, a multiple choice and a free response portion. Now the multiple choice part, you will get 90 minutes to do roughly 70 questions, so quite a few questions. If you target about a minute a question, you'll be in pretty good shape with lots of time to go back. The second part of the test, the free response, is somewhere between 6 and 8 questions usually, and you'll have 90 minutes for that as well. So what we're going to do is we're going to start with the multiple choice. We'll split it in halves. We'll do 35 questions first, then we'll stop, take a break, do another 35, and then we'll come to the free response. Now, as you do these, a couple things. Don't leave anything blank. You don't lose any points for a wrong answer. So you might as well guess. And if you can narrow down, eliminate a couple of the wrong answers, the odds of getting that right answer go way up. But also, don't feel like you have to answer every question correctly. You can miss quite a few questions on this test and still get a very, very good score. So with that, why don't we dive into the multiple choice part of the test? I would recommend, instead of just watching me as you answer the questions, why don't you take something like 45 minutes or so, try to go through the test on your own, and then come back and we'll see how you did as we go through it. So, taking a look look at all the answers. You can eliminate a couple of the answers just by looking at the units of angular momentum. On to number 7. 3 forces are acting on an object. If the object's in translational equilibrium, what do we know? Well, translational equilibrium, all of the forces must sum to 0. The net force must be 0. Also, the acceleration then is going to be 0. So what is our correct answers? Well, number 1, absolutely that's correct. Number 2, no, the magnitudes of the forces don't have to be equal. They just have to sum to 0, so that's not it. And number 3, the forces must be parallel. Yeah, it's just silly. So our correct answer must be A, 1 only. All right. Number 8 looks extremely similar to some of the graphs we drew when we were talking about energy back in our energy lectures. And what it tells us is we're given a graph of the potential energy. We need to figure out the kinetic energy. And remember, the kinetic energy is just the inverse of the potential energy as long as you have a constant total energy. So a very familiar graph in physics. Here we have our potential energy. Looks kind of like that. And we know in this closed system, we must have a constant total energy. So what's going to happen? Well, when it's not potential, it must be kinetic and vice versa. So our kinetic energy graph is going to look like we have here in purple. That's our kinetic energy graph. So the correct answer there must be that's not it. Davison-Germer electron diffraction experiment. Yes, absolutely. If you recall Davison-Germer experiment, we had 2 slits. We shot an electron, or electrons toward it, and then we looked on a screen behind it, and we observed a diffraction pattern, evidence that electrons behave as waves. So that must be one of our correct answers. And 3, Thomson's measurement of the charge to mass ratio. Well, important work, but really didn't have anything to do with proving electrons are waves. So the correct answer is going to be 2 only, or answer B. Number 12. What quantities are conserved in nuclear reactions? Well, let's think. We've got all of our conservation laws. Number 1 is going to be charge. Charge must be conserved. So 1 is a correct answer. Number of nuclei and protons, I don't recall any laws about conservation of nuclei or protons. So our correct answer here must be 1A. And 13. We're looking at an uncharged conducting sphere in a uniform electric field. So let me draw our electric field. We'll say it's pointing in that direction. And in it, we will put an uncharged conducting sphere. Well, because it's a conductor, the electrons in that conductor are free to move. They're going to line up along with the electric field. So we're going to have the electrons want to go opposite the direction of the electric field. They're going to try and hang out over there. That's going to leave positive charges on this side. So you're going to have a force. You're going to have a force from the electrons in the electric field and the protons in the electric field. But because it's a uniform electric field and the entire conducting sphere is in it, resistance must be less than the smallest resistor in that parallel configuration. So R equivalent, my equivalent resistance must be less than 2 ohms. Looking at my answer choices, I only have one answer that's less than 2 ohms. Answer A. Didn't even have to go calculate it. Number 16, we're working with the same circuit. It asks if there's a steady current in the circuit, the amount of charge passing a point per unit time. Well, that's current flow. Current flow is what we're looking for. What's going to happen? Well, we're going to get the most current through the branch with the smallest resistance. So that's going to be, that side is going to get the most current flow. So we're going to have more current in this resistor than we are in this network of resistors, which is actually broken up into a 1 and a 3 ohm resistor, but they'll have the same current because they're on a series path. So without a doubt, we're going to have greater current through the branch with the smallest resistance, so E must be our correct answer. It's going to be greater in the 2 ohm resistor than the 3 ohm resistor. All right, Number 17 and 18 have to do with that diagram where we have two positive charges at corners of a square, and the lengths are side D. And we want to find the direction of the net electric field at point P. Well, let me just redraw this a little bit. For number 17, we've got some charge that's plus Q, some distance D away. Our point P is our point of interest. And over here, we've got another charge plus Q. If we want to find the net electric field at P, well, let's figure out the electric field due to this charge plus Q. That's going to give us an electric field away, so we'll have at P, it'll be pointing this way. And over here on our plus Q charge to the right, that's a positive charge. The electric field points away from positive charges, so at P, that's going to point that direction. When I add those together to get the net electric field, I have and our magnetic field strength, B, well, that's just going to be 2 Tesla. Our area is the length times width of our rectangle of wire. So that's going to be 0.05 meters times 0.08 meters. Therefore, my flux is going to be, well, 2 times 5, 0.05 times 0.08 is going to be 0.008 Tesla meters squared. Or if I want to write that in scientific notation, that's 8 times 10 to the minus third Tesla meters squared. Or answer choice C. Let's take a look here at number 20. Talking about a coffee pot tells us the current that it draws, its potential difference that it requires, and also tells us about electrical energy costs. We have 10 cents per kilowatt hour. And if you recall, kilowatt hour is a unit of energy. So we need to figure out how much it's going to cost us to run this device for 2 hours. Well, the way I would do that is I would start by taking a look at the power that we have here. If power is IV, which is also equal to work divided by time, I could rearrange that to find the work, or the energy, is going to be equal to IVT, which is going to be the current flow through our device, 4 amps, times the potential difference, the voltage, 120 volts, times the time. And I'm going to leave this in hours since we're after an energy in kilowatt hours. This implies then that the work, or the energy, 4 times 120 is 480, times 2 will be 960 watt hours. But we want kilowatt hours. All right, well, kilowatt is 1,000 watts, so that's pretty easy to convert and say that that's going to be 0.96 kilowatt hours. Now our answer, we need to know what the cost is going to be to operate it. So let's take our 0.96 kilowatt hours, and we're going to convert that into a monetary unit, because we know that 1 kilowatt hour is 10 cents. So my units here, kilowatt hours, are going to make a ratio of 1 or cancel out. 0.96 times 10 is going to give me an answer of 9.6 cents. Therefore, the correct answer here would be D. In 21, we've got an electron in a uniform magnetic field. And as it's moving in the plane of the page, we need to find the force on the electron. This is a right-hand rule problem. However, it's a negative charge. So we're going to use our left hand. Point the fingers of your left hand in the direction of the electron's velocity, and then bend them in the direction of the magnetic field. You should see then the direction of your thumb pointing in the direction of the force. Fingers of your left hand in the direction of the electron's velocity. Bend your fingers in the direction the magnetic field points. Your thumb should point A toward the right. All right. For 22 and 23, it looks like we've got a PV diagram from our thermodynamic study. We're talking about a couple different processes here, and asks which of the following is true of the work done on the gas. Well, remember, the work done from a PV diagram is the area under the graph. And if it's done on the gas, we must be going to a smaller volume, to the left of that PV diagram. So which one of those has the greatest area under it as we move to the left on the PV diagram? That answer must be number 1, or A. And for 20 that boundary. All right, well, we know V equals F lambda, and the frequency remains the same. Now, as you go from one material into another, the different index of refraction, the speed of that electromagnetic wave is going to change. And as you go from air to water, it's going to slow down. So if our velocity is decreasing and frequency is constant, that means wavelength must be decreasing. So the answer that gives us a decreasing speed and a decreasing wavelength is answer E. Oops, don't want to skip any here. Number 28. We've got a student doing another optics experiment here. Going to place an object 6 centimeters from a converging lens, so the object distance is 6 centimeters, and our focal length is 9 centimeters. Find the magnification of the image, the magnitude of the magnification. Well, we'll use our equation again. 1 over f equals 1 over do plus 1 over di, to find that 1 over 9 equals 1 over 6 plus 1 over di. And I'm going to rewrite that as 1/9, that's 2/18, equals 1/6, that'll be 3/18 plus 1 over di. All right, that makes it pretty easy to see then that 1 over di must be negative 1/18. So 1 over di equals minus 1/18. Therefore, di must equal negative 18 centimeters. Once we have that, the magnification test, you do that with a straight edge to make sure that you're as accurate as possible. But if you look, right away we can see we've got a real image because the light rays are actually converging where we have our image. It's inverted, and it is magnified. So the correct answer here would be D. It's real and magnified, larger. All right, 31. We have a light ray passing through a few substances, and it shows the index of refraction of those, and it tells you ray segments 1 and 3 are parallel. Well, if it's parallel at 1 and 3, right away with Snell's law, we know 1 and 3 must have the same index of refraction. So N1 must equal N3. We're pretty sure of that. Now, as it goes from 1 to 2, it bends toward the normal. That means N2 must be greater than N1. I don't see that as any of my choices. And then as it goes from N2 to N3, well, it bends away from the normal. That means N2 must be greater than N3, which of course makes sense if N1 and N3 are equal. But as I look at all those choices for answers, the only one that works out looks like it's going to be A. N3 is equal to N1. Couple more here. 32. We're talking about a radioactive sample and it's decaying at a rate of 4,000 counts per minute. At 12:30 p.m., that rate has decreased to half what it was before. So find the predicted rate at 1:30. Well, what we're really talking about is a half-life here. And it looks like our half-life must be 30 minutes because the decay rate cuts in half every 30 minutes based on the information that's given there. So I would say that at noon, we had 4,000 counts per minute. At 12:30, we had half of that, 2,000, which means at 1, you must have had 1,000. And then at 1:30, you probably had 500. And it asks you what the decay rate is at 1:30, so the answer there must be B, 500 counts per minute. 33, a little bit more nuclear decay. We've got a negative beta particle and a gamma ray emitted during a radioactive decay of some lead. Let's see what this is going to look like. We've got 214-82 lead, and it's going to decay by negative beta decay plus a gamma ray, and we're going to be left with something left over, X. Let's see if we can't fill these in a little more detail so we know exactly what's happening. 214-82 lead is going to be, well, our beta decay, that's going to give us -10 E. We've got our gamma ray, and then we've got this X. But what do we know about the X? Well, if we've got 82 here, -1, that must be an 83, and we still have 214 nucleons there. So I really don't know what element that is offhand, but as I look at my answer choices, I only have one answer that has 214 as the mass number and 83 as the atomic number, and it looks like that's bismuth, which is answer choice D. All right, 34. We're talking about the momentum of an electron and figuring out what happens to its de Broglie wavelength. Well, let's start by writing the equation lambda equals h over p for the de Broglie wavelength. And it's saying if the momentum doubles, well, if we multiply that by 2, then over here, 2 in the denominator, we've got to have 2 in the denominator over here. So what happened? We have half the wavelength we had before. Answer B. And one more here. 35. Talking about quantum concepts being critical in explaining these different things. Well, Rutherford scattering experiments, those were all about showing that we had a small positive nucleus, we had orbiting electrons, and the atom itself was mostly empty space. Nothing in there really relates to quantum phenomena. So right away, I'm betting the answer's A. Bohr's theory of the hydrogen atom, well, that's all about quantum theory and energy levels. Compton scattering, that's about quantum theory and momentum of a photon. The black body spectrum, well, that was evidence of the particle nature and had to do with quantum effects. And the photoelectric effect, absolutely about energy levels and quantum effects again. So our answer there must be A. Rutherford scattering experiments have nothing to do with these quantum concepts. All right, I think we're going to stop there for the first half of the test. Give you a second to catch up. Recommend going through, making sure you understand these answers. And if you don't as you go through them, go back to the previous portions of the lectures, of the videos, and see if you can't pick up on it. So when you come back to these, you go, yeah, I've got that down pat. We'll do part 2 of the test here in our next, part 2 of the multiple choice in our next session. Thanks so much for your time, everyone, and make it a great day.